curves, x cubed plus c, that are being generated on top of the slope field. Now taking a look at example 1a, we have a derivative. Again, a derivative is a slope machine. And if we look at this derivative, we're noticing that the derivative is defined in terms of x and y. And if you go back to chapter 3, it was not uncommon for us to find derivatives that had x's and y's in them. And if you recall, we did derivatives implicitly, and we used implicit differentiation when I had an equation that had x's and y's, and it wasn't real convenient to get the equation solved for y in terms of x. So here, kind of curious to know what function has this derivative. Wouldn't be easy for us to anti-differentiate, which again is the scope of what we're going to do second semester. So we're going to just kind of go along and we're going to generate a slope field. And again, we have a lot of points here on our coordinate grid. In terms of on the AP exam, they will not give you this many slope fields to do. So here we've got 4 by 4 in quadrant 1. So we have 16 locations here, 16 in quadrant 2, 16 in quadrant 3, and 16 in quadrant 4, as well as the x-axis and y-axis. So while this may seem like a lot of work to do, you're going to be looking for trends. So I'm going to pause this. I'm going to give you a moment to look at finding the instantaneous rate of change at these many locations. And then we're going to see if we can make sense at what function would have this derivative. So again, pause the video if you would, and at least try to get kind of a trend of what the mini tangent lines are going to look like at all these different locations for x and y. Alright, here we go. We're going to reveal the slope field. We're going to see how you did on this. So revealing the bunches of mini t's that we have, you might have a better idea of what function could have this derivative by looking at the slope fields. Now you're going to notice here at the origin that I'm going to leave that blank. Again, right here, if I put in 0 over 0, that's undefined. So wherever you have 0 over 0, I would leave the slope field blank. At the point 1, 0, I'm drawing in a vertical tangent at 1, 0, 2, 0, 3, 0, 4, 0, as well as over here on the x-axis. And the reason why is I'm taking a constant, I'm dividing it by 0. That's going to indicate a vertical tangent. And again, if you weren't sure, you could plug in a point 1 and you could put in a tenth. So if I put in 1 and I divide it by a tenth, it's going to be getting infinitely large. And so that's going to indicate a slight trend to decrease, but being very vertical. So here's our slope field, and that's what they had asked that we do, that we could determine the slope field for the following derivative. But if you look at this, hopefully what you're noticing is that we have a bunch of circles that are going to follow the trend. So again, if they gave me a point, which they are in B, they're saying, hey, sketch the solution curve that goes through the point 2, 2. Obviously, I'm going to go right 2 and I'm going to go up 2, and I'm going to have a point going through this mini tangent. And that's going to mean that the curve is going to have to go through and be decreasing much as the tangent line is showing. So as I go up, I'm going to begin to circle around, and I'm going to end up right back where I started. So at the point 2, 2, if you follow my finger, we're going to follow the mini tangent lines going around, and we're going to end up right back here. So this was an interesting derivative that we're finding the family of functions that has this derivative, which actually be circles centered at the origin. So what family of functions could have the derivative above? X squared plus y squared is equal to r squared. This is our general formula for a circle centered at the origin. And if we do find the derivative implicitly, the derivative of x squared is 2x. The derivative of y squared is 2y times y prime. And obviously the derivative constant is 0. Solving for y prime, we do get negative x divided by y. So an interesting derivative that we were able to find the family of functions. x squared plus y squared is equal to c, and doing the derivative, we get the stated derivative. Interesting. Now, hopefully you got a bunch of good programs from me on your TI-84. If you're an Inspire user, you're not going to be in luck here. You'd have to look to see if you can find anything online to do slope fields with your calculator. So what I'm going to do is go through some tips for you. So again, we found dy dx to be negative x over y, and we are going to type that into y1. So if you look right here, we're going to put the function into y1, and we're going to use alpha key to type in the y value. So I'm going to hit y equals, and I'm going to clear this out. I'm going to type in opposite of x. So the opposite of x divided by alpha y. So let me find that on here. There we go. And so I'm going to put that in first into my calculator under y1. It's important that you put it into y1. And the other thing that's going to be important is that you're going to want to change your window. And so this is going to be really critical to make sure that you make your window smaller, wherever that may be. And again, I would suggest that you only use this program to check. Typically what we see on the AP exam is that they're going to give us problems like this to do without the technology. So the good thing about this program is it's going to allow you to see if your slope fields are being constructed correctly. So I'm going to go to Window, and for us, going from -5 to 5 I think was sufficient. -5, 5, 1, -5, 5, 1. So I'm going to go there. I'm going to hit my program key. I'm going to go down to slope fields. I believe it's this program right here. We'll give that a try. And how many marks across? Let me pause this. So here we go again. I went to my program key. I'm going to go down to SF. And that is my preferred slope field program. I'm going to hit enter, slope field. And again, y1 is going to be my derivative that we just typed in. And again, with my viewing window going from -5 to 5 along the x-axis and the y-axis, I am producing many t's at all my designated coordinates in this window. And that does model what we had done in example 1a very nicely. Okay, so here is your assignment for day 1. And again, you're going to have a copy of this. Here are some tips for you in terms of doing slope fields, ways that you can make it go quickly. Here they're giving you an example, a derivative is cosine of x, and of course we know the function that has this derivative. And looking at this, hopefully you can see the vertical shift of the sine curve going up and down. Taking a look at the bottom of this assignment, what I don't like about some of these illustrations is it can be kind of hard for you to tell what the slope field is showing here. So again, what they're asking you to do is to match these with the differential equations. So again, what you're going to try to do is play the matching game and seeing which slope fields match the stated derivative. I wish these had windows on them for you to look at. So just give this your best shot and to see if you can do the matching game. The problems that follow I think are better because the windows are clearer for you. Here is the next set of exercises that again is going to go through. They give you quite a few slope fields. You're going to want to again do many t's at each of the designated points. And again, you're going to see some that are explicitly defined in terms of x, others in terms of y, and some that are in terms of x and y. You're going to construct slope fields for all of these problems. Now on this page, they have done the work for you, and you'll look and you'll see, wow, that's great. They've given me all these slope fields. And down here, we're going to play the matching game once more. But notice that these are not derivatives, these are functions. So again, what you're going to want to do is play the matching game and to state which slope field would match this function where the function is always equal to 1. So what would that slope field look like if this were my function? So this is different than the previous set of problems where we were constructing a slope field based on knowing the derivative. Let me know if you have any questions on that, but this is something that you'll typically see on the AP exam as well. On the next page, we're playing the matching game once more. Just this time, what are we looking at? We're looking at derivatives. And then these two on the bottom, great questions that are kind of taking things to that AP level where they're giving you the derivative, they're giving you the slope field, and then they're asking you to sketch a point that goes through the point 0, 2, and 0, -1. So here they're showing you what a potential function could look like if it went through the point 0, 1. You're going to draw two more. Do label A and B with the curve so I can tell that you do have the right curve going through for A versus B. Down here, again, we have the slope field constructed, and you're going to draw a curve to represent the function that contains the point 0, 1. And you're going to draw a curve going through the point -3, 0. Again, using your slope fields to generate a curve containing that. So good luck on slope fields day 1. I will follow up now with day 2.